Okay, hello everyone. Welcome to Astronomy 405. Today in next lecture, we're going to take a brief digression out of the solar system to talk about kind of give our solar system some context by looking at other planets that are not in our solar system. Sometimes the best way to do a comparative work is to look at things to compare it to. So first off, we are talking about detection of exoplanets, and then we'll talk about results and kind of some statistical stuff and properties of exoplanets. So today's goals, we're going to describe all of the methods we have to detect exoplanets, and there's a lot, but the two of them are have been the most successful, and we're also going to talk about their biases, the method biases. An exoplanet or extrasolar planet, it's a planet that orbits a star other than our sun. As of April 16th, there are 4,100 confirmed exoplanets. And we've only been at this for under 40 years. In 1988, so that's only 32 years ago, Campbell et al. Observed a possible planet, Gamma Cephei AB, but they couldn't confirm it. They were thinking this may be a planet. They retracted and that retracted the data, then they unretracted it in 2003. In 1992, Wolfskin and Frail announced the first planet, but it's a bit of an odd one. It was a planet around a pulsar, a neutron star. In 1995, we got the first planet around a sun-like star with Mayor and Queloz. And again, now, as of April 2020, we are up to over 4,000 of these things, and that's just the ones we've confirmed. So let's look at how we discover these. And the first set of methods is going to be using the gravity of the planet. All of these methods are going to rely on the fact that the planet and the star orbit their center of mass. We often simplify this by saying the planet orbits the star because the center of mass of the system is close to the star. But what is actually going on is the planet is orbiting the center of mass. So let's start with those first few planets, the pulsar planets, because those are weird. Pulsars are spinning neutron stars. Rather, magnetic poles are putting out jets, which give us a bunch of beamed radio waves. We see these in the radio sky with a radio telescope as a periodic flash of radio waves. And it's very regular. The analogy we often use are lighthouses. Even the rate of change is often pretty regularly. Now, if the planet is orbiting a pulsar or anything, what is going to happen, and we see this picture on the bottom with the sun and Jupiter, is the two objects are orbiting their center of mass. Now, since the planet is much less massive than the star, what happens is the planet is making a very big circle, but the star is making a little small circle. Now, for the pulsar, what we can do is the light travel time from that pulsar changes over one orbit of the planet. That means that some of the pulses are going to come early if they're on the near side of the orbit, and some of the pulses will come late if they're on the far side. And there'll be a very periodic thing telling us that this pulsar is kind of wobbling back and forth. Now, we can do this because pulsars are really regular. We can't do this with a sun-like star because this light travel time is on the order of less than a second. So we need something that is reliable to less than a second, and pulsars are. So this is from the original paper. The top plot is the residuals for the pulse arrival time, just raw, corrected for the pulse, just take off when we predict it to happen based on the average, and then subtract that off, and we get a bunch of bumps and wiggles. And it seems to have some kind of pattern. It does not seem to be random. You could kind of imagine maybe a sine curve or two in that. So we fit a sine curve saying, okay, assume this thing is wobbling back and forth in a circle. We can fit a sine curve to that. And B and C fit two different sine curves. And you can see each of them takes out part of the variation. So now the remaining looks a lot like a sine curve. So you could imagine adding B plus C to get A. And then D is the final residuals after taking out those two sine curves, which are caused by two planets. And you can see those are much smaller. A through C are plotted in terms of milliseconds, which are not, not trivially small units, but D is plotted in hundredths of a millisecond. So we can't do that. We don't see many pulsar planets. This system is unusual, but which makes sense because these are planets that either survived a supernova or formed after one, because that's where you get the pulsar, the supernova. And there are actually 3 planets in this system, though the third planet is quite small. It is the smallest exoplanet we know about, which gives you the power of this method, even though these are not very useful for comparing. These are really interesting and weird planets, but they're not very useful for comparing to the Earth. Let's get the problem. So we need some way to do this with sun-like stars. So how we do this with pulsars is we are seeing the projected orbit of the pulsar as it moves around the center of mass. We're measuring only the radial distance because the movement of the pulsar out in the we're measuring the line of sight, what's going on in the line of sight. That is what's affecting the light travel time. The movement in the plane of the sky is small enough that we're not seeing it. And we can basically approximate it as not happening. So what we need the planet's period, and we can estimate the mass of the pulsar, and we need to estimate the mass of the pulsar. Now from the planet's period and its mass, and the pulsar mass, we can estimate what the semi-major axis of the orbit is. And once we have that, we can get how far away the pulsar is from the center of mass, which will tell us the mass of the planet. Now, the problem is we're only sensitive to the projected orbit of the pulsar. We're only sensitive to the line of sight motion. So that angle I marked on the graph is a free parameter. What it ends up doing is it limits, the pulsar mass we find, or the planet mass we find, is actually the planet mass times sine I. So we have only a minimum mass. All right, so what if we want to do this with a normal star? Well, we need, again, a way to measure the star's motion around the center of mass of the system, the barycenter. And if we're doing it like the pulsar, we can do it line of sight. So similar geometry to the previous picture. There we can't use light travel time because we don't have a nice clock on a normal star, on a main sequence star. But we have the Doppler effect. That means if the star moves towards us, we have a blue shift. If the star moves away, we have a red shift. That if the star is moving back and forth, that should be a periodic signal. We can use that to get the star's radial velocity. And again, that will be periodic based on the planet's orbit. It'll repeat. If you just have one planet, it'll repeat every orbit. If you have 2 planets, you have 2 periods buried in there. Once we have the period's orbit and we estimate the mass of the star based on our knowledge of stellar properties, we can get the semi-major axis of the orbit. And then what we can do is once we get that semi-major axis, once we have that amplitude of radial velocity and the orbital period or the semi-major axis, we can get m sine I, mass of the planet sine I. Now, the limits of this method is that most stars are rotating, so they have Doppler broadening because when you have a rotating star, one side is moving towards you, one side is moving away from you, which broadens their lines. They have temperature broadening in the lines. So in order to get an average to figure out to not be tricked by the near side of the star moving towards you and the far side moving away from you, you have to observe many lines. Usually what happens is you have to observe something like 1,000 lines to subtract the motion of the star's rotation and get what is the center of the line doing? So this rules out a lot of hot stars, which is a shame because they're really bright. But thankfully, they're also really rare. Cold stars, like red dwarfs, are challenging just because they have so many lines that the lines start to be on top of one another. And they also start to get molecules in their atmospheres, which don't produce nice, sharp spectral lines. They produce broad absorption bands. And they're also pretty dim. So kind of thankfully, the sun-like stars are actually kind of in the sweet spot. So that's the radial direction, the towards away direction. But we have the line of sight directions. Right ascension, declination. So what we can do here is what's called astrometry. Astrometry is precisely measuring the position of stars. We do this often to find things like parallax or how much the star is moving, proper motion. We have seen that binary stars show this motion. They show that the center of mass of the system is what's obeying Newton's laws. It's moving in a straight line or an orbit around our galaxy, which under short periods can be approximated as a straight line, and the two stars are moving around their center of mass. It's not as useful to find planets because the motions are really small. So this is a diagram of our sun and what the solar system center of mass does relative to the sun. So you can see it mostly stays either within the sun or within about a solar radius of the sun. And most of this motion is Jupiter and Saturn, and it changes very slowly. Jupiter's orbital period is about 12 years, Saturn's is about 30, so you get kind of this loop-de-loop pattern as the two planets influence the star, with lesser influences from the other 6. But it's all happening over decades, so you need to be able to measure this star's position really precisely over decades, or even more precisely over a shorter period of time. Now, the Gaia mission is a space telescope. It is designed precisely to do this kind of work for many, many different projects, but it should help us find some planets. And one of the nice things about the astrometric method is that the pulsar timing and the radial velocity give us m sin I. We're only seeing one dimension, so we can only get a minimum mass. The planet is directly aligned with our line of sight, is directly moving towards and away from us rather than slanted. Astrometry is giving us 2 dimensions, and if we couple it with radial velocity, we get all 3. So that means we can fit the full orbit and get at the inclination of the system, so we know exactly what the masses of our planets are. Again, it's really difficult to do. We only confirmed a few handfuls of systems that we know had radial velocity results, and then look for astrometry to either conform an orbit or set some limits. We've only discovered one planet this way. That's the various gravitational methods. We're using the fact the star is not at its center of mass and is moving around relative to that because it's got planets, which means that the center of mass is a little bit offset of the system is a little bit offset from the star.